After you take a class.
And it's more than just a primer, it's like good examples.
Exactly.
And we're live. Amazing about this. Since there weren't a lot of, I don't think anybody new is with us who missed the 9 o'clock class, or at least had most of the 9 o'clock class, and I did review most of that. So I won't bore you. That's all online anyway now, so it's all, whatever swear words I did and whatever admissions I did from a prior life are all in the record there. So we'll move on. So explain my numbering system on these title charts a little bit. Mondays was sort of an introduction lecture. I'm counting that as lecture 0. Lecture 1 was our Wednesday lecture, and that's actually on the course echoes part of e-learning. And so you should be able to see that again if you need to, but I think everybody's seen it. And then the lecture 2 we had at 9 o'clock this morning. That would be the Wednesday lecture coming up. Now we're into the week after next, which is lecture 3. So I'll just sequentially number these lectures as we go along. And we're continuing our review of signals and systems. Okay? And I should put AM there. Yes, sir. Did you have a question? No. Oh, I saw your hand go up, and I wanted to make sure you... Okay. So, we were talking about some of the functions. I reminded you of the sines and cosines and the relationship to the complex exponentials, and therefore all exponentials. You can go the other way. You probably have heard of hyperbolic sines and cosines. So that's exponentials represented as, with their own version of Euler's relations. So we're talking about a more subtle function, which is the delta function, the Dirac delta function. I pointed out that it's a singularity that has zero width and infinite height, but the area is equal to a finite number, and typically we like to, and this is where I use the word normalize, we'd like to normalize that to 1. Okay, we'd like to normalize that area to 1. Now, delta functions are a very general concept. If I take any lump of signal, any pulse of signal, any lump of signal, I can push that towards a delta function. I can start with any shape of pulse, and I can push it towards a delta function. And an example of that, one way of thinking about this is if I have, let's suppose I have a beach ball. Okay? This is a spatial example, not a time example. But supposing I have a beach ball, and I blow up that beach ball so it's a big sphere. And I'll say it's a boring beach ball. It's painted only one color, red. Since I picked on your shirt before, I'll pick on it again, or I'll celebrate it this time. So I have this red beach ball. Okay, so it's Saturday morning, mid-Saturday morning. It's a nice topic to be thinking about, a nice red beach ball. And if I go very, very far away from that beach ball, it begins to look smaller and 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 smaller until it becomes just a little point of red. Okay? And at that point, we can say that it looks like a delta function, a little spot, a little point. And it really didn't matter if I started with a red bowling ball, or a red beach ball, or a red planet like Mars. If I get far away from all of those spheres, far enough away from all those spheres, they look like a point. They look like a little delta function located in space. Okay, but we're going to talk about delta functions located in time. That's a much easier thing to think about. Not much harder, not much easier to work with, but much easier to think about. And so, any pulse will tend towards a delta function. So, Gaussian pulses, Lorentzian pulses, hyperbolic secant pulses. In which case, so to keep it simple in this class, Isn't it nice the way professors, when they lecture, always take the simplest example, and then homework is so much harder than that? It's a conspiracy that we get to participate in, and I quite enjoy it. I kid, sort of. So I'll take a square pulse here, and what I'm going to do is I'm going to label the pulse width is equal to A. And I'm going to let the height of this equal to 1 over A. Okay? And now if A gets small, the pulse width gets smaller. But 1 over A, if A gets small, that goes higher. So what I'll do is I'll draw that a little bit more. And that's for, let's see, I guess I'll make this A prime. That's for A prime greater than A, right? Nope, other way around. That's for A prime greater, less than A. Okay, so the pulse gets smaller. And by the way, the pulse right this time right in the middle is time t equals 0. So I'm plotting this in the time domain. Okay, and the center of that pulse is 0. So now if I let's say I'll double 1 over A, or I take 1 over A in a half. You can start to see how this delta function progression goes. I construct a pulse so that the area is equal to 1 over A, that's the height, times the width, which is equal to 1. So this area under the curve is the same as this area under the curve. Is the same as this area under the curve. And if I keep going, I get a delta function. And that's nice because this product here, this area, is independent of A. Yeah. So that's just a simple construction for a square pulse, or for a rectangular pulse, on how we get a delta function from that. And you can now infer that, okay, now I have a Gaussian, or I have a hyperbolic secant, which is a very nice pulse, by the way. You should write that down. Hyperbolic secant pulse. It has some really nice properties. And so on. They will all tend towards delta functions. Okay. The only thing you might want to think about when you're doing this normalization is what exactly we mean by a pulse width of those distributions. And to which I'll remind you, I won't go into it in great detail, but I'll remind you that if I have any distribution, I have the average value, and then I also have the first moment. I also have the moment, higher moments, which would be the standard deviation, or the width, or the variance. And so I can relate the standard deviation or that first moment to a pulse width. And that's probably the most reliable, nice way of considering a distribution. The width of a distribution would be that first moment. Okay? I also have second moments, third moments, and so on. But that's probably enough for now. Okay? And of course, we'll be very sloppy when we consider widths of strange distributions like the sinc function. We'll be sloppy about that. But if you want to be more careful about it, then remember what you've learned in probability statistics, where you're going to take standard deviations and so on. If I have to define what a delta function is mathematically, one way of doing that is to point out that it's 0 if time is less than 0. It's also 0 if time is greater than 0. And it's infinity at times t equal to 0. And that's this picture that I've drawn here. It's 0 out here, it's 0 out here, and it's infinity right only at that point, t equals 0. Okay. If I take the integral, this is not quite enough. If I take the integral of delta of t over all time, minus infinity to infinity, that's well behaved, that's equal to 1. And what that suggests is the way to tame the singularity, the way to tame that singularity, that nasty integral, that nasty infinity sign, is to put a delta function and anything else you would want to consider with it underneath that integral. So this is not just a property. It's not just a property that says what part of a delta function. It's not just it's also a recipe for how you can handle and how you can work with a singularity of a delta function of infinity. So it's a very, 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 very useful tool. It's not. It doesn't look that way when you just write it that way. But when you think about what you can do with it and what it does is it gets rid of that singularity. It can do that in a lot of ways. Okay? And the specific value of the 1 just means that it's a well normalized delta function. The other thing I wanted to kind of just remind you of this, is if I connect these two guys together, I have the integral from minus infinity to 0, or maybe actually a little bit before 0. So I'm going to write that as 0 minus epsilon, or just 0 minus. And then I have an integral, and then I have another integral, which is from 0 just a little bit beyond the delta function. So that's a 0 plus an epsilon, or just more sloppily, just a 0 plus, all the way to infinity. And then the missing piece is right around the origin, and that's 0 minus to 0 plus del of t, dt. And that's going to equal a 0 plus a 1 plus a 0, those three integrals. Okay? So the purpose of that is to show you how you handle the delta function right around 0, and to introduce this notation that you may have seen before of 0 minus and 0 plus. And what I mean by that is 0 plus, 0, and 0 minus, just around the delta function. Okay? So if I go back to my beach ball, it's just a little bit to the left of the beach ball and just a little bit to the right of the beach ball. Okay? And of course this comes into play if I have a function, f of t, and this function, for whatever reason, meets a delta function. If for some reason I happen to have a product, a mix, a collision, an overlap, a product between a delta function and an f of t, we're going to spend a lot more time on multiplications of functions in this course. Modulation of f of t with delta of t. How's that for a communications term? If I have a product between delta of t and f of t and I want to understand what this is going to be, then I tame it with the delta with this integral. And so I have f of t, delta of t dt from minus infinity to infinity. And I'll write it in this manner. So that's going to be an integral from minus infinity to 0. Help me out?
Minus.
Perfect. Good. And that's f of t times whatever the delta function is. That's delta of t. That's 0 of t. Plus the integral from minus infinity. From 0 minus to 0 plus of f of t. And I'm going to leave the delta function in there, because I'm not sure quite how I'm going to handle that just yet. And then plus another 0 plus to infinity of f of t times, I know it's going to be 0 dt. So that guy goes to 0 and that guy goes to 0. That makes me very happy. This makes me very sad. So I've got to think about what that means. And so I look at my figure and I scratch my head a lot. And I look at this figure and I say, well, gee, okay, this f of t is wiggling all over the place. It's a nice function. That's its job is to wiggle all over the place. However, right where the delta function is, if that delta function is 0 width, it has only one value. It's only the value at that point. And so now if I look at this integral, well, this integral is the value of f of t at t equals 0 times that delta function. And if this is just a constant, I can pull that out of the integral. And this guy here is equal to 1. So this is called the sifting property. And what it says is that the integral from minus infinity to infinity of f of t del of t dt is equal to f of 0, or wherever the delta function is. Mm-hmm.
So it's not like you're finding any constructive interference. It's like you're taking a sample or like reading at that certain time of the original signal.
Yeah, I like those words a lot. I'll even put them on the piece of paper. That's exactly right. That's exactly right. And again, so you know, all I'm doing is just going through the mathematics, and then we look at the math and we say, what does it mean? And you summarized it brilliantly. I appreciate that. And let me also just we talked about shifting in time, right? And so let me just write down one other thing: f of t delta of t, and then let me just say I'll move it by some period or some capital T, some offset capital T, dt. And if you go through exactly the same analysis here, you'll have t minus and t plus, capital T minus and capital T plus, and so this will equal f of capital T. And now that you see is now you happen to use the word sampling, right? So now we see, well, if I make this some integer value of that sampling period, then I can get a stream of values out every integer number of capital T. And so that is exactly a methodology of sampling that waveform. And if I sample that continuous time waveform, I have a discrete time. Not a digital signal, but a discrete time signal. Okay? So, and we'll study that in a lot more detail. I mentioned this last time. I'll just write it down and then we'll forget about it this time. If I integrate that delta function, if I integrate that function, I get a delta function. I'm sorry, if I integrate that delta function, I get a step function. Notice the treatment, I'm using a dummy variable of integration t prime because I have an indefinite integral t. Okay? I didn't have to worry about that so much when I had definite limits, minus infinity to infinity, but now I'm accumulating, I'm doing an average that it runs over, and so I have to worry about my variable of integration. I mentioned last time, and I'll just mention again, that if I integrate the step function, I get a ramp. Integrate a ramp, I get a quadratic, and now I can generate all my Taylor series, all my polynomial expansions that way. And that's a very powerful technique. Now this is can anyone see there's something aesthetically wrong with the step function. There's something aesthetically wrong with the step function.
There's no period?
It's got an infinite slope at 0.
Well, it's always going to have that. And that's actually a really good point, right? I start with a singularity. The position, the magnitude of delta function is infinity. When I integrate that, I still have a singularity, and it happens to be the slope, right? If I integrate this and I get a ramp, I still have a singularity. It's a slope discontinuity. So all I'm doing when I integrate this is I take my singularity and I just move it to another bin. Right? I just shuffle it out of the way just a little bit more. Okay. So yeah, you're right. The difference is of course a kick and versus a kick followed by steady pressure on this, an abrupt push. But there's something that bugs me about this, and if I say parity, does this have parity? No, it doesn't have parity. And so to fix that, in this course, what we're going to do is we're going to slide this down. We're going to slide this down. And this has parity. Pardon? Oh, no, wait a minute. Did I? Oh, screwed up the paper.
Oh, yeah.
Sorry. I thought you said I should slide the step function up. And I'm like, wait, no. So I moved the step function down. I moved the paper up. And so now I have this side here. And this line here it does have parity. It's what kind of parity? Odd parity, right? I have to flip it around the axis, time reversal, and then flip it up one more, or rotate it in a diagonal, depending on how confident you are on those operations. And that's almost what I want. In fact, what I really want is not a half here, but a -1 and a 1. At least that's by convention. And if this is the step function u of t, then this function, this new function, which we made just by shifting the step function, is called the signum function of t. The signum function of t. Like a step function, but with parity, odd parity. Okay? And so that's going to be a very useful. Having that parity there is going to be very, very useful, because you know that if you Fourier transform things with parity versus without parity, there are theorems that govern what to expect on that. And it turns out nicely that those consequences actually have great physical meaning. And so we will leverage or exploit the heck out of those things when we start to do some advanced AM techniques, for example. Okay. Now, all this stuff So the delta function, as you've learned about in signals and systems, is very useful in characterizing systems, particularly linear time-invariant systems. Okay? So if I take any kind of a system and I drive it with a delta function, I learn something about it. And what I mean by that, I used to do this all the time. Whoever sat there was at grave disadvantage, because I would point out that this desk is a spring mass system. It has mass on it, and it has spring constants and how things are joined together. And so if I kick it, it's going to rattle around for a while and then decay back into shape, into quiescence. And that's the delta function response of that spring mass system. So if I've got inductors and capacitances in my system and resistors, I kick that system with a delta function. I put in a little bit of energy, a unit amount of energy, and that energy gets passed from capacitor to inductor, lost in the resistor, back to the capacitor, back to the inductor, and so on and so forth, until all of it damps out to zero, and the resistor has eaten all of the energy. Okay? And just again, to push that a little bit more back into the physics world, you know that energy has two types of energy, kinetic energy and potential energy. And you know that the capacitor, because it's static charge across the plates of that capacitor, that's potential energy. And that as that charge moves through the inductor, moving charge, that's kinetic energy. So 1/2 Li squared is current, is the energy, the kinetic energy that goes through the inductor. And 1/2 CV squared is the potential energy that gets stored on the capacitor. Okay? So that's sort of the energy distribution. Oh, and then the I squared R, or the IV that goes on the energy that's on the resistor, that's energy that leaves the electrics and goes into thermal heat. So that's energy is robbed out of the electrical part of the world and moved into the glowing heat that makes your toast in a toaster. Okay. So, but anyway, all that stuff is going on when we consider a system and that initial. Providing that initial little burst of delta function energy in, showing out what happens, tells us a great deal for systems, and in particularly linear time-invariant systems, because it allows us to predict the response of any other signal that I put into that system. So if I take my LRC circuit, or I take my spring mass system, and I characterize it with a delta function energy in, then I know the wiggles of that desk, or I know the oscillations of my R or my C to any other kinds of signal that I put in. 2 delta functions, 20 delta functions, a step function, sinusoids, exponentials, Gaussian pulses, hyperbolic secant pulses, anything I want. Sums of sines and cosines. Oh my gosh, is that a Fourier series? Not yet. We haven't gotten there yet, but it will be. Okay. So the diagram that you're very used to looking at is a system, and maybe it's a device under test, or system under test, something that a bud box, a gray box of we might give you this in the lab and say, all you know is there's resistors and capacitors in there. Figure out the values of the resistors and the capacitors. We probably don't do that experiment because it's way too much fun. But that is a classic experiment that you might imagine us doing. Sounds like a good test question.
Figure out the amount or figure out the values?
Pardon?
Figure out the amount or figure out the values of?
Both. Everything. And just to push the fact a little bit, maybe all I do is I say that it's a linear time-invariant system. Okay, so it's made up of simple components. I'll get to that, what that simple means in a little bit. And maybe there are no resistors and capacitors in there at all, but maybe the complete model of that linear time-invariant system, or that system assumed to be linear time-invariant, maybe that model is constructed in terms of resistors and capacitors and inductors, even when there's none of those in there, because it's a mathematical model. Okay? Maybe what's in there is some little transducer that turns the electrical signal into a faithful analog representation of physical forces on a spring mass system, and then another transducer that takes it back out into so that it's a voltage and a current. In which case you would be modeling that spring mass system as a set of LRC circuits, when in fact physically, because you couldn't open it up, you wouldn't know that it wasn't. Okay? And think about that if you think about your physics, your differential equations class, and you studied LRC circuits, and you studied spring mass systems with a dash pot, and they were both the same equation. And so the mathematical model of those didn't discriminate on the physical realization of those. And since you can't tear apart this box, you're thinking you only have my word that there's resistors, capacitors, and inductors on there, and you should know me by now not to trust my word, right? So what you're doing is you're abstracting. You're saying that if there were resistors, if there were resistors, capacitors, and inductors, if McFarland was saying the truth, then this would be the model of the system. It could be a DSP.
So you're saying there's transfer functions of different systems that are identical. You can't really know. Yeah. It's
very much a mathematical abstraction. It's very much a mathematical abstraction. But it also goes to digression. It also goes to the layers of your design, right? You have the abstract mathematical description, and I'll be specific, of your comm system. Okay? And this is where a lot of the coding theory people live. This is where a lot of the advanced theoretical people live. This is let's say 80% of our course is going to be the mathematical manipulations that describe AM, FM, and so on. Then right below it, you have the physical realization of that comm system. And so this is what you build and sell, right? This is what you build and sell. This is the description of it. And you'd like for this description to be very close to that, but it won't be when you first start inventing. When you first start inventing, you're going to have an idea for a better mathematical abstraction, and then you're going to hunt around and you're going to say, how can I realize that element? How can I realize that arrangement of elements with real parts that I can buy from DigiKey or from Newark or Edmunds Optics? Okay, and so that becomes your physical realization. And every time you go component to component here, or block to component here, you're making an abstraction. So a spring mass system doesn't act exactly like a resistor or capacitor. If you have a spring mass system, it'll rattle. There might be impairments like nonlinearities that are different than they would be if it was a capacitor. A spring might behave differently in extreme regimes. So there's a disconnect between here. You want one to be the other, but it won't exactly line up. And the reason I point that out is again, I want to show you what the elements of the modeling problem that we're working on in comm systems, and I also want to show you where difficulties can arise. The difficulties can arise from the abstract mathematics. Once you've sorted those out, you're still not home, because then when you realize that you've got a whole bunch of physical realities, physical impairments, physical limitations for those guys. So you make an assumption about how a transistor works here, and you guys know enough to know that transistors don't work perfectly to the models as you build them. Right? And so that's where these levels of difficulty can kind of come in a real comm systems problem, a design problem. And again, I find it useful if you know where difficulties can come from. It's easier to work your way through them, and that's why I bring that up as a digression. Okay, sorry. Anyway, so I've got this device under test. I have an input x of t, and I have an output y of t. Okay, and the problem is one problem. There's many problems associated with this silly little diagram. One thing is, if I know what x of t is, can I predict what y of t is?
Give a little more information that you could.
So that's an issue. That's one thing you would like to know. And if I have a y of t, can I predict what x of t gave it to me?
You need a little more information, but
Figure
it out.
Pardon?
Like a feedback?
Nope. I'm just saying a single input, single output. If I know what y of t is, can I guess what x of t is? In other words, if I have a thermometer that's somewhat impaired, and it makes a reading of a temperature that says the temperature is 97.4, and it's really 98.6, can I recalibrate that to get the right answer? Okay. Maybe I can, maybe I can't. Maybe I lose information, maybe I don't lose information. I don't know. But again, these are the problems that we would like to face with this, right? Another problem is what's in the device under test. What's in the black box? What's in the bud box? What's going on in there? That's a third area problem, and that's your characterization problem. What model describes that? Okay. So here's an interesting model, and it's related to communications. I give a lecture, x of t. You guys walk away with a perception of that lecture. Okay? It's very, very important to me to understand, if I say something, what you mean by it. Okay? It's not. It's critical for me to try to understand where your background is from, what you actually took out of certain previous courses, how you use words like normalization and how I use words like normalization, so I can work with that, and I won't say you're wrong, but I can shift you into my way of thinking for the purposes of these lectures only, so that what I say is a more faithful representation. But that would be a signals and systems model for teaching, right? So, and it's a comm system. So anyway, I bring that up. Okay, so if x of t goes to y of t, then there's two aspects of this. I'll do the time invariant first. Okay? These are two properties of that system, time invariance and linearity. They're separate. If x of t goes to y of t, and x of t minus a, some small shift, goes to y of t minus a for all a, then time invariant. Then the system is time invariant. All a. Okay. So, I know I'm probably off camera by now, but it's so much fun to do. I kick the desk, it shakes. I kick the desk at 11:10 in the morning, right? If I kick it again at 11:30, it'll wiggle exactly the same way. When I kick it again at 1:15, it's exactly the same way. When I kick it again at 1:55, it'll be exactly the same. At 2, I'm giving you warning, by the way. But you see what I'm saying? Whenever I hit that. Now, what happens if I kick it so hard that I break it? then it's not time invariant anymore, is it? Right. So there are clearly limits. There are clearly limits to this whole business of time invariance. But that's basically what we're saying is, and that's exactly half of this magic LTI system that you spent so much time in your signal systems class that you probably think that all systems are linear and time invariant. And what depraved individual would ever start asking you questions about systems that were not linear time invariant? Well, you're looking at him. Okay, so that's one of those issues. All right, now that's the first one. The second one is this linearity, the L part of this whole equation, and if xi of t goes to yi of t, and I can find two signals, or for any two signals, and I add them together, a weighted average together, weighted adding together. So I have a cosine and a sine, or I have a delta function and an exponential, and I scale one up or down, I scale the other up and down. If the output is a y1 of t, xi goes to yi, plus b y2 of t, x2 goes to y2, then we say this is what?
Scale.
Linear. Yeah, scalable is these scaling factors, and then additive is the superposition. Superposition. In fact, that's such a good word. I'm going to write that down. This is a weighted superposition. Okay. So that describes that's what linear time invariant means. Okay. Now, if I whoops, there we go. If I give you this mythical Bud box, this one of these gray aluminum boxes made by the company Bud that you've stuffed electronics in when you're hobbyists, then how do you know what's inside of there is a linear time invariant system? How do you know that you can represent it by a spring mass system or by LRCs?
You compare the input with the output and see if the first output is time invariant and then secondly find it if it's linear.
Okay. That sounds very simple. That sounds very simple, doesn't it? But how would you, let's think about that, let's think through that in practice. You want to look at the time invariance first or the linearity first?
Just do time invariant.
Okay. So I got this Bud box, and I interrogate it on a Monday. How do I interrogate it?
Interrogate it next day.
No, but how do I first decide what I'm going to interrogate it with? X of t.
You can run a signal through it.
So maybe I look at my I go up to the lab and I say, okay, I've got a function generator, and I'm just going to turn the knob to be every single output of that function generator. And that sounds like a pain if you're turning the knobs by hand, but maybe what you do is you hook it up to LabVIEW, and you write a LabVIEW script to go through, apply all the cosines, apply all the sines, apply them at all frequencies, apply them at all from -10 to 10 volts. Then you do the triangle waves, then you do the square waves, and all the different frequencies there, and all the different amplitudes there. And you can get your LabVIEW script to run that pretty fast while you go off and have a cup of coffee, right? And you're pretty happy. And then you do that again if that's your Monday work. You do that again on Tuesday. You do that again on Saturday. Are you satisfied?
Maybe, probably not.
What happens if somebody invents a function generator that has new squiggles on it, Gaussian pulses on it? You haven't tested for that. right? And how do you know you've waited long enough? Communication systems are designed for 20-year lives, for 20-year lifetimes, which means if you sell into AT&T, somewhere along the way, you're sort of doing something to attest to the fact that this communication system will still be good in 2 decades. If you think that's bad, one of the markets for undersea cables, undersea fiber optic systems, is to network the oil rigs in the North Sea or in the Gulf of Mexico. And when you sell into the oil companies to do that, do you know what reliability factor they want? Do you know what lifetime they want? 100 years.
Essentially forever.
No,
Oh,
just 100 years.
amazing.
Those are. I think this is a comm systems course, right? So that's one of the requirements of communication systems.
Wouldn't it be cheaper for them to utilize anyway? But also, if you're running infinite tests for your sample, as you said earlier, if you break the sample,
Yep.
obviously not going to work on
Yep.
Saturday.
Yep, that's very true. You can wear the sample out. You can wear the sample out. Just think about a simple resistor, right? In the old days, you would make a resistor, with a piece of paper that you smeared with some carbon on it and rolled it up around a tube, and that was your carbon resistance. For high voltages, these things were about a foot long. I don't know if you've ever seen this, about a foot long and painted ceramic brown. And they were little tubes and stuff, and they were high voltage resistors today. And back in the day, they were the normal way of making resistors. Well, carbon and paper, how long do you really think that's going to last? So there are lifetime issues. Now, when we say time invariant and we want to be sensible about it, what we really mean is that if we wait a few reasonable cycles of our system, it's the same. In other words, if I kick the desk, okay? If I decide that I'm going to kick this desk for 2 minutes, and I start kicking it for the first 15 seconds, and I want to kick it for the last 15 seconds, what I mean by time invariance is across those 2 minutes of which of interest in the problem, the desk is the desk is the desk. That's really what I mean. That's a much more sensible definition for what I mean by time invariance. This business of reliability is a very different issue. Because what I can do is I can write a script, I can concoct a test plan. If I am selling to the oil companies, or I'm selling to AT&T, what I can do is I can say, I know that my resistor values are going to change, but what I will do is every Thanksgiving, once a year, every Thanksgiving, I am going to test all the elements. I'm going to run a test signal through them. I'm going to test all the elements, and I'm going to recalibrate my system for you. And that way, I'll adjust the weights of my DSP chips. I'll adjust my time constants and everything so that your system will be continuously tuned or readjusted or recalibrated every so often. And so there I have a time varying system, but it's irrelevant because once it's in calibration, it'll hold forever. And so that's one way of handling this. Reliability data also demands see if I remember right. 80 degrees is the hottest temperature you have to design to, and I want to say probably 0 degrees is the coldest temperature that you have to operate at. If you design a system at room temperature, 20 degrees, it's not going to run at 20 degrees when you shove it in a rack in a point of presence. And then similarly, if you're going to put it in a curb unit, one of these units that sit out by the curb, it's not going to run. You could see 100 degree Fahrenheit days, 140 degree Fahrenheit days, and minus 40 degree Fahrenheit days. And so how do you handle that? Well, again, calibration, recalibration, temperature sensors, shifting all that is one approach, one very, very good approach to doing all that. Okay. Anyway, so time invariance. That's a time invariance problem. What about linearity?
Oh, how you test for linearity? As you said, you utilize different signals. And so what happens when you scale it?
Scale them. So you apply a sine wave at 1 volt, at 2 volts, at 10 volts, at 20 volts, and you know that it's not going to be the same at 100 volts. But what you do is you say over this range it's going to be linear. So that's how you get around that. And there's no other real way of doing that. That's the only way. That's really the only hope you have to do that. So again, it's perfectly fine when we say it's an abstraction, but when we start going into the physical realization of that abstraction, we have to get limits. Okay? And again, part of the digression, the second digression, the one I didn't write down, is just how stringent some of these comm system requirements for liability is. It's, really, really interesting. All right, now, so that's a very difficult. Turns out that's actually a very difficult task to characterize these and determine what the limits are for linearity. Again, because if you break it, you can't go back and unbreak it. Maybe, So once you've found the limits of linearity, maybe it's still linear. Maybe it returns to where it was before. Maybe it doesn't. Hysteresis. Okay. The way I like to look at it is that a linear time invariant system can do only two things. If I apply a cosine, omega t, to a linear time invariant system, the only thing it can do, in fact, let me write this a different way. If I have a linear time invariant system and I apply a cosine of omega t, the only two things that it can do is change the amplitude, change the phase. That's a really powerful statement. The only two, and you can think about this with respect to LRC circuits, with respect to passive elements and so on. The only things that they can do is change the amplitude. Maybe they can make them bigger if you have gain in it. More likely they're going to attenuate, make them smaller. You're lucky in an LRC circuit if it leaves the frequency component alone. And it can shift the phase. It can delay it. It probably can't get it out faster. It probably takes time to move the signal through the wire. Probably something like a foot a nanosecond or 8 inches a nanosecond if you're in a wire. That's very fast, but if you've got many inches, or you're working at very high frequencies. But it'd still be a delay, a phase delay, and an amplitude change. And so if you can one approach is you decide your function generator. You decide what values of input voltages you can put into it, and then you sweep your cosine for over all frequencies that you have. So you interrogate at 1 hertz, at 3 hertz, at 5 hertz, at 10 hertz, at 20 hertz, at 50 hertz, at 100 hertz, at 200 hertz, at 500 hertz, at 1,000 hertz, at 2,000 hertz, 5,000 hertz, 10,000 hertz. Why did I go that separation? 1, 2, 5, 10, 20. On a log scale, those are equally spaced on a log scale. And if you notice on your oscilloscope, that's where the detent values are. Okay? So it's a little shortcut if you know what you're going to plot, right? All right. So The only thing a linear time invariant can do is change the amplitude and the phase, and so if you characterize those amplitude and phases for all frequencies, you're home free. That leads to two observations. One, if you see new frequency components from the input to the output that weren't there before, then you don't have a linear time invariant system. And to me, that's the fastest experimental way of determining the nonlinearities. That's the fastest experimental way of doing that. One example of that. Think about a speaker, not a person, but a loudspeaker. Okay? And if you think about the old or the big analog loudspeakers, not the little PZT things that we have that are so wonderful, it still works that way, but it's easier to visualize. What you have is you've got a little electromotor. You apply the music onto it, and it moves the cone up and down through a range. Right? The faster the frequency, the faster the cone wiggles back and forth. And the louder it is, the more the cone works back and forth. So if I take my hypothetical opera singer who holds that A note for 20 minutes, and I start, the cone vibrates on the A note, somebody smart can tell me what frequency that is, right? 440, thank you. So 440 hertz, I never remember that. I'm not very musically inclined. But 440 hertz is the cone movement, back and forth, back and forth. Perfectly reasonable because it's moving the compression waves in the sound in the atmosphere, and your ear is picking that up and responding to it at 440 hertz. And so now, I crank the gain up on it because it's such a beautiful melody. So I crank the gain up on it. And now the cone, it was moving, let's say, a centimeter. It now tries to move 3 centimeters. But my travel is only 2 centimeters. Well, if that's the case, there's my input. There's my output. It's clipped off. It's half of the waveform is gone. And see how sharp see how sharp that bend is? That's a slope discontinuity, right? That's a slope discontinuity. And the Fourier series of the black line is a cosine, 440 hertz. The Fourier series of this distorted black line, the red line, the distorted signal, is 440 hertz plus 880 hertz plus 1320 hertz, and so on and so on and so on. The harmonics all come in. So the input here is 440 hertz. The output here has a 440 hertz in it, but some of the signal gets scattered out into the higher harmonics. Okay? And so this is harmonic distortion. New frequency components came out from this lack of linear response of the speaker. If I want to characterize how good a speaker it is, what I can say is how much power, what's the amplitude of all these spikes, add them up all together, what's the amplitude, what's the power, and what's the percentage of that to the power that I come in. And that's a specification that you have on all the speakers, and that's the harmonic distortion, the level of harmonic distortion. And so you would pay more for a level of harmonic distortion of 1% than 5%. Okay? Because you've run out of travel, or maybe the cone isn't mounted right, And so it sort of jostles in there a little bit. It wiggles. It doesn't go perfectly back and forth. It wiggles around. Okay? Abstraction between the math and the physical system. So, to me, this is a very, very nice experimental signature of whether or not you have a linear time-invariant system, is if you see new frequency components or not. You know, I can't resist. You know those laser pointers that have the nice bright green? You know laser pointers that have red, right? The laser pointers that have red, if you rip those apart, they have a red laser diode in there. Right? That stands to reason. It's a laser pointer. It has a laser in there. It's a laser diode, small little chip that emits, 670 nanometers. I forgot exactly what they usually use for that, but probably 670 or 640 or 620, depending, The green laser pointers, you would be unsurprised if I said that there was a green laser diode in there, but there isn't. The green laser pointers actually have a diode laser at 1 micron, not at 0.67 microns, but at 1 micron. It goes through a magic crystal. The crystal is designed to enhance the nonlinear response, that harmonic distortion, so that an appreciable amount goes from the 1 micron to the half micron. From the 1 terahertz to the 2 terahertz. I'm sorry, I have that wrong. From the 3 terahertz, more or less, to the 6 terahertz. So the 300 terahertz to the 600 terahertz. I think that's pretty close. You can check me on that. From 1 micron to half a micron. And half a micron is smack dab in the middle of your spectrum, your eye spectrum, and it's that brilliant shade of green. And I'll tell you, for someone who, grew up on optical tables, trying to get that green light out of a 1 micron laser, YAG laser, to see that almost given away, the green laser pointers given away with that nonlinear experiment just embedded in there, is really cool. And it really shows how far along the optics world has gone in the last couple of decades. I mean, it's just phenomenal. So you can imagine, it's amazing that you can have your laser in there. You can have your optics, you can have your nonlinear exotic crystal, and you can get a brilliant amount of green light out of that by completely saying, I don't want a linear system, I want a nonlinear system, and I want it as nonlinear as I possibly can get it, because I want new frequency components in there. Okay? So, that's one observation. The second observation has to do with this interrogation. And remember what we were saying was, you take your function generator and you hook it up to LabVIEW, and you program it to go all these different frequencies. And you make some approximations so that you don't have to do 99.999999 hertz. You limit your number of decimal places. But you have to do that. Now, the other way you can do that is, what happens if I want all the frequency components to go in there at once? I need a signal in the time domain that has equal representation of all the frequency components. And what do we call that function? Step function, but there's actually a better one that does it, related to the step function. If I want to fully characterize this system, what function do I put in? Impulse function. Right? Because an impulse function has each and every frequency components in it, right? In the time domain, it's a spike. In the frequency domain, it's a flat line. So it has embedded in it every single frequency component's in there. And what will come out will be, for each of those frequency components, in one measurement, it will be the change in the amplitude and the change in the phase of those frequency components. And we call that the impulse function response, H of t. Okay. By the way, if I'm doing this with a discrete time signal, I have almost the same notation. A delta function in and an h of n out. Okay? So that's my second observation from that magical fact that, you know, a linear time invariant system only does a certain number of things to my input signal. That's my one observation of that. Okay? And that shows, that argues, and you've seen this picture a million times, right? You've seen this picture a million times in signals and systems, and now I'm trying to give you a richer understanding of why exactly that's so magical. And it's premised on the fact of what we know about delta functions and the frequency response, and what we know about linear time invariant systems and what they do to the frequency responses. Okay. And also in the time domain, if I want to think about it in the time domain, then, well, I'll hold off on that for a little bit. So now, if I have the linear time invariant system, and if it's characterized by h of t, and now notice that this is this is interesting, right? Because what I've done is I have a system, my gray bud box, full of components. And now what I'm doing is I'm saying, okay, I'm going to represent that system by a function or a signal. So am I talking about a signal or am I talking about a system? It's getting blurred, nicely blurred, which is another reason why we get to call that course Signals and Systems. And it's because that we purposely wanted to start blurring that line. Maybe that's confusing to you, but maybe we're doing that and you didn't realize we were doing that. But that's what we're doing. We're putting a fast one on you. Okay. So there's h of t, and then we go back to our original problem, which was I have a system under test, and if it's linear time invariant, I want to know this x of t and y of t. Or if I'm in discrete time space, I have a given input sequence. I have the delta function input sequence. I have the output sequence there. What are the relationships between x and y? If I know x, can I predict y? If I know y, can I estimate x? Yes, no, maybe, to some approximations, so on and so forth. But that's more or less where we are. And actually, that's a pretty good place to wrap this lecture up. What I'll do is I'll try to, let me try to get this in order here a little bit. I'll just flip through these slides real fast so you can kind of get a sense of them. We started off looking at the delta function, where delta functions come from. Any pulse can be focused into a delta function. Properties of the delta function. I have these backwards. Mathematical representation of the delta function. Notice the singularity gets tamed with the integral. How do you represent that? You can integrate out and get a constant area. Introduction of 0 plus 0 minus. I get the sifting property coming from that, which allows us to do sampling, something that's going to be really, really important when we do pulse code modulation. And also because it takes from a continuous time to a discrete time. Not a digital signal, but a discrete time signal. Relationship to the step function, ramp, quadratic, and so on follows nicely. And introducing a new function that's just like the step function that we call a signum function. And if you take a look at through Lati, he really likes the signum function, and the reason we all like the signum function is because of the parity, the definite parity that it has. Something sloppy about that function that doesn't have parity. One of the things that you might want to do for fun tonight, it's Saturday night, so you look for a little bit of fun. You might take a look at this slide here, and you might try to write down what exactly the signum function is in terms of U of t. You know that you have this factor of 2 scaling in here, and you know you have to subtract down by some amount. So use some of the properties of scaling and so on to get that to working. The delta function in terms of their interaction with systems. And we started by starting with the linear time invariant system, what it meant to be time invariant, what it meant to be linear. We had a lot of nice digressions about what that, what the limitations of that are. Don't get me wrong, it's a very, very good place to start if you have this unknown system to say, I will assume for now, till my money runs out or till my time runs out, that it is in fact linear time invariant. And here's what I can learn if it's linear time invariant. And then I can start shopping around and saying, what are the nonlinearities associated with it? Okay? This is very, very fundamental. Only 2 things an LTI system can do to a sinusoid. And sinusoids are invariably one of our favorite functions, so knowing this is really important. Everything interrogating, as soon as we have a sine wave generator, a function generator, we open up the door to this. The role of new frequency components in nonlinearity, and the delta function response. Okay. The delta function response to an LTI system is very special. And it's very special because in one fell kick, we are providing all the frequency components, and we're mapping what's happening to the amplitude and the phase. We're going to find out what happens to the amplitude and the phase. So this flat line here is going to wiggle around. It's going to have dips in it, maybe rising in it, and at every one of those dips and rises, I'm going to have a phase shift. Okay? And once I have that delta function, this is our starting point for what's going to happen after lunch. Okay? All right. Quit there.